Welcome to The Explainer. Today, we're going to tackle a concept from AI called likelihood weighting. Now, I know it sounds complicated, but trust me, stick with me here. By the end of this, you'll see how a problem that looks really intimidating is actually solved with some surprisingly simple logic.
Okay, let's just dive right in. This is the kind of thing you'd see in an advanced course, and at first glance, yeah, it can look pretty overwhelming. You've got this network, all these probability tables, a bunch of sample data. It's like, where do we even start, right? But if you strip away all the noise, the question itself is actually pretty straightforward. We've got this network that shows how different things influence each other, and our whole mission is just to figure out the chances of A being true, given that we already know for a fact that C and D are false.
So the very first step to cracking any problem like this is to separate what you're trying to figure out from what you've already been told. It's all about finding the question and the clues.
You'll see this P of query by evidence notation all the time. It's just a formal way of asking, hey, what are the chances of our query happening given the evidence we already have? It's what's called a conditional probability. Basically, it's all about using the clues you have to find the answer you need. So in our problem, it's crystal clear. A is the query. That's what we're curious about. The evidence? That's minus C and minus D, the clues that tell us C is false and D is false. And honestly, getting this distinction right is the key that unlocks the entire problem. Okay, now we get to the core idea, the secret sauce, if you will. How do we actually use our evidence to make sense of the sample data we were given? Well, this is where the weighting part of likelihood weighting comes into play. The goal here is to give each of those samples a score, or a weight. And this weight is basically going to tell us how consistent that particular sample is with the evidence we already know to be true. And here's the best part. The logic is beautifully simple. There are just two rules, that's it. Rule 1, if a variable in a sample is not part of our evidence, its weight is just 1. We kind of ignore it for now. Rule 2, if a variable is evidence, like our C and D, its weight is its probability, which we just pull right from the tables. Seriously, it's that straightforward. So, enough talk, let's put these two simple rules into practice. We're going to calculate the weights for each of our 3 samples, one by one. First up is sample 1. So, in this world, A is true, B is false, C is false, and D is false. And let's just keep our evidence in mind. We know not C and not D are true. Let's break this down. For A and B, are they evidence? Nope. So their weight is 1. Easy. Now for C. Is it evidence? Yes, it is. To find its weight, we look at its parent in the network, which is B. In this sample, B is false. So we go to our tables and ask, what's the probability of C given negative B? The table tells us it's 3/5. We do the exact same thing for D and find its probability given negative B is 1/5. Now to get the total weight for the whole sample, we just multiply those numbers together. So 1 times 1 times 3/5 times 1/5, which gives us a final weight of 3/25 for our first sample. All right, moving on to sample 2. Notice the big change here. B has flipped from false to true. This one little change is going to affect our whole calculation. But the process is exactly the same. A and B get a weight of 1 because they're not evidence. But now because B is positive in this sample, we have to look up a different row in our probability tables. P of negative C with positive B is 2/5, and P of negative D with positive B is 1/2. See how that works? We multiply them all out. 1 times 2/5 times 1/2, and we get a nice clean weight of 1/5 for sample 2. And now for our final sample, sample 3. In this one, A and B are both true, and our evidence variables minus C and minus D are of course still there. Now, since B is positive here, just like it was in sample 2, the math for our evidence variables C and D is going to be exactly the same. And remember, the value of A doesn't matter for the weight calculation at all, because it's not evidence. And that gives us a weight of 1/5 for sample 3 as well. Great, we've now got a weight for all of our samples. We are on the home stretch. The heavy lifting is officially done. Now, all we need to do is combine these weights to get our final estimate. So let's just lay everything out so it's easy to see. Here are our 3 samples, the weights we just calculated, and a note on whether they're consistent with our query, which was A being true. You can see samples 1 and 3 are yes, but sample 2 is a no.
And this brings us to the final formula, which is actually really intuitive. To get our estimate, we just add up the weights of the samples that match our query, and then we divide that by the sum of the weights of all the samples. It's just the ratio of the matching weights to the total weights.
At this point, we're just plugging in the numbers we already found. So the weights for samples 1 and 3 go on top, and the weights for all 3 samples go on the bottom.
And there you have it. We've turned a complex-looking problem into some pretty simple arithmetic. But this isn't just a math trick. This is a foundational technique for how AI systems actually learn and reason. You know, when an AI system is diagnosing a disease or filtering spam from your email, it's doing a much, much more complex version of this exact process, taking in new evidence and updating its beliefs about the world. It all comes back to this one simple, powerful idea: weighing the evidence.